Well, our next speaker is Luca Del Pero. He's going to be talking about real-time camera localization for AR assistance in complex environments.
Hello everyone, thanks for having me here. I'm currently head of computer vision at Blipper, which is a company based here in London, and our main focus is on augmented reality. And today I'd like to show you our recent work on how you can use augmented reality to turn a physical space, like an office or an airport or even an entire city, into a smart and digital environment. Imagine, for example, if you could navigate and explore a city in augmented reality. Like, for example, if you could see directions to your destination through your camera feed, or say you're in this square and you point your phone around and you point it, for example, to this ship here and it tells you what ship it is and information about it, or you point it at the building and it tells you what restaurants and shops are in it. And so essentially, these are all examples of what we call location-based augmented reality, and the key concept here is to have a digital layer to appear in front of the physical location the user is at. And we think that if this could be done at scale and robustly, this is a potential change in the way we interact with the physical world. Just as an example, today if you're in front of a restaurant and you want to find reviews about it, you would type the name on a web browser. Whereas here you could just point your phone at it and the information, the digital layer will appear in front of the physical building and you will see it there. So today I plan to show you some example of our current tech for doing this type of things, and then I will dive into the technical challenges which are mostly in the domain of computer vision, because in order to do this you need to be able to do pose estimation in large and complex environments. So before I dive in, I just wanted to give you a quick overview on Blipper. So the company was founded in 2011, and in the early years the main focus was on marker-based augmented reality. Essentially, marker is a planar surface with some texture. Here you see a cereal box. It could be any food packaging. It could be a book cover. And the idea is pretty simple. You point your phone at it. The system recognizes it. It can do real-time pose estimation and then show some AR content. For example, here it's turning the cereal box into a board game. And this has been and still is a pretty important part of our business. And we had a lot of campaigns with major brands using this type of tech. And more recently, we moved to a different type of AR, which it requires more involved types of visual recognition that go beyond marker recognition. Here you can see that you can use the Blipper app to recognize famous people or the make and model of a car. In the parking lot, you see other things like logos, flowers, and landmarks. So essentially, visual recognition is another big area of interest for us. But let's go back to the main topic of the talk, which is something we started to work more recently. Again, it's what is called location-based AR, and we think it's going to be a pretty hot topic in the next few years. So what differentiates location-based from standard AR is the fact that the digital content is tied to a physical location, where it could be the facade of a building, it could be an aisle of a supermarket. So it requires recognizing exactly where the user is and which way they're pointing their phone to present the digital content at the right place. And this content has to be persistent, which means that it has to be available to all users that are at that location at any time. And so anytime the user points their phone at that ship, they have to see the same information at the same exact location. And the key technical challenge, as I mentioned before, is to be able to do pose estimation in this environment, where it's an airport to the right, or whether it's that square or an entire city on the left. And I'll now show you an example of this tech that we developed. This is an app called AR City. It's available in beta on the App Store. And essentially, the idea is very simple. This works in 300 cities, including London, so you can try it out. you start the app and it goes straight through the camera, and it estimates your pose within the city, so in a way that it can overlay a virtual map. Let me just go back a little bit. It overlays a virtual map on top of the physical, where you see the street and their names, and you also see addresses and points of interest that get displayed on top of the physical world. And the main thing you can do is to do navigation. Oops. So essentially, you type your destination, and the direction will appear through the camera, and then the user can start following them. And so we think it's a nice thing that you don't have to know how to orient the map anymore, since the directions you can see them overlaid onto the world. And one of the main challenges we have to solve in AR City, but this is true for no matter what environment you're working with, whether it's a city or a shopping mall, is that you need to know exactly where the user camera is and which way it's pointing. So compared to a lot of the talks we've seen in the morning, here the camera is moving with the user, as opposed to having to reason about the environment from static cameras. So we have to do 6 degrees of freedom pose estimation. Essentially, it's estimating 6 parameters. The three indicate the position of the phone in the environment, and then you have the 3 rotations of the phone coordinate system with respect to an absolute reference frame. The meaning of the position can be slightly different depending on where you are. In a city, it makes sense to talk about latitude and longitude and elevation. Maybe in a shopping mall, you can imagine having a Euclidean system with X, Y, Z, and this could be X, Y, Z in that coordinate system. And this has to be solved quite accurately, because if I estimate my pose with and then a meter off, say, then the digital content will appear in the wrong place, and the user experience will be bad. And this needs to be solved at every frame as the user moves around, so that the digital content sticks to the world, and it has to be real time, relying on the computational power that is available on mobile devices. And this is a very high-level overview of the pose estimation engine that we're trying to build for location-based AR. And it has essentially 2 components. One is a method to estimate the pose of the phone of the camera with respect to an absolute reference frame. And we use many different signals for this. A trivial one is to use the GPS, which can tell you your current latitude and longitude, and the compass that gives you your heading with respect to north. These obviously can be very noisy. One that is very popular in the literature now is to use computer vision to solve this problem. And you can imagine you have a data set of geotagged images with an underlying 3D model, and you get the camera, the image from your phone camera, and you leverage this data set to estimate the pose from the image. And this is a much more involved process than just using the GPS. It's more computationally expensive, but it can achieve a much higher accuracy. And then there's other things you can use. There's in airports sometimes you can find Bluetooth beacons that can give you a reasonable estimate of your position. So one signal that we use here is absolute pose estimation, and the second one is relative pose tracking. Essentially, this is a way to determine how you move from a starting point. It's essentially your local relative movement and your local relative delta in rotation. And modern phones provide this as a module using visual inertial odometry. That's the name of this type of algorithms. And this is provided on Apple by a framework called the ARKit, and on Android devices by a framework called the AR Core. And these 2 frameworks generated a lot of interest recently. And you might wonder, why do you need both these 2 components? Well, the absolute pose is, you might think, why can't I use my absolute pose estimator at every frame? The problem is that this can be either too computationally expensive, so you cannot run it at every frame, or it cannot pick up your local movement in a way that is fine-grained enough to keep the digital content at the right place. For example, the GPS can pick up that you move by a meter, but you need to pick up the small movement that you do to keep the digital content at the right place. This is what relative pose tracking gives you. It can give you a nice fine-grained estimation of how you moved to the level of centimeters. It is also real time. It has also shortcomings. It's subject to drift. The more you use it, the more error accumulates. And it also has no concept of an absolute coordinate frame. It only estimates your relative motion with respect to a starting point. And here is just a very quick high-level intuition of how you can combine them. We need an absolute pose estimator to initialize your location and orientation, and then you can rely on relative tracking. But this will be subject to drift, so you need to consult your absolute pose estimator periodically and integrate the two systems using their uncertainty to do it in a principled way. And this is the picture version of the absolute pose estimators that we could use. The trivial one is GPS and compass, which is a very cheap computationally but has a large error. And all the way to the bottom right, where you have a full database of geotagged images covering an entire city with an underlying 3D model that allows you to do pose estimation with computer vision and can be very accurate. And some more details on the relative tracker, which again estimates your delta in translation and in orientation, and it combines inertial sensor and computer vision on device to pick up your local relative movement. And I'd like to just give a quick intuitive version of how you can combine these signals. So here is what would happen if there was no noise in any of the sensors that I use. So the blue dots are observation from the absolute pose estimator. This could be GPS or it could be localization via computer vision. And you can see that they are quite spaced. There's quite some space between each other. And the red arrows denote what the relative tracker, the movement estimated by the relative tracker. And you can see that they nicely fill the gaps in between consecutive observation, and since there is no noise, everything is aligned perfectly. But in the real world, there is noise. So you can see here that since the local tracking starts to drift and also the absolute pose estimator can have noise, there are disagreements between the local tracking and the absolute pose estimator. You can see, for example, here that due to drift, the red arrows are not agreeing with this observation at all. I'm also drawing uncertainty. So each of these measurements has some uncertainty. So the key question is how to deal with this disagreement. Well, there's several ways. One way we use is a Kalman filter, where essentially your local tracker acts as a velocity estimator, and your absolute pose estimator acts as observation. This is quite principled, but it needs to have accurate uncertainty models of all the components in your system. And the second method, which is I'm just going to use here as an intuition to show how this could work. It is very simple. You're just making sure that your current estimate is never outside of, say, 1 or 2 sigmas with respect to your observation. So in this is just an enlarged version. So in this case, in the case of this observation here, your current hypothesis goes through. It is contained within the uncertainty, so there is no problem. Whereas in this other case, it's falling outside, and so you can shift it up like this to make sure it at least agrees with the uncertainty bound. And in doing all this, you have to do it. Maybe you should try to be as smooth as possible. You don't want your pose to change too much across consecutive frames, otherwise the user will see objects jump in front of their eyes. And then this is just the last measurement, which is fine. And here is like a concrete example of what I was showing. So here this is the trajectory of a user for which we know that they walked on the left side of this road. So to the right you see the trajectory estimated by just listening blindly to the GPS, and you can see that there's quite a lot of error. The user according to GPS, the user has walked on the wrong side of the street, and if you use that to display AR content, it will be all out of place. What happens to the blue line is instead we initialize the system with the first reading of the GPS, and then we let the local tracker take charge without looking at the GPS ever again. And what's happening here, you can see it starts to drift a little bit right away. It's not too bad, but then it starts putting the user in the wrong place. It puts them inside the building rather than on the street. And the green is the combination of the two sensors, and it actually is following the user path much more accurately. And are we doing on time? Finish. Okay, so I'll just skip this one. As a recap, I just showed our pose estimation engine for AR, which can turn a physical space into a digital environment. And one of the examples that I showed was using the AR City app, which allows you to do exploration and navigation in a city. And then we also have an indoor version. This is the last thing I'm going to show. So what you see here on the right is the raw camera feed, and in the big screen you see what the user is actually seeing, and you can see that we changed the content. So you see here there is a wall, but our content creator decided that they wanted the user to see a different texture on this wall. In this case it's a wooden texture, and as the user moves around, that's what they'll see. And I'll just play the video. So it starts here with like a rubber duck on the river, these sort of things. And as the user walks around, the pose estimation keeps running. The content sticks to the right place. If, for example, we put some graffiti on that wall at the end. And the application for this are very many, and we have, in particular, navigation is something that we're receiving a lot of interest in. And I just would like to thank all the people who have been involved in this and then take any questions.
So how big issue is actually the scale drift for you have a bit more of
Sorry, can you say it again?
how big issue is the scale drift if you have also camera?
So the drift, if you listen just to the local tracker, can be